Welcome, everyone. The title of my talk is Incorporating Constraints into Learning from Demonstration and Motion Planning, as Brad just said. Just to give everyone a brief, brief history of time. So fourscore and about 14 years ago, I started at UC Santa Barbara, eventually graduating with a biopsychology degree. And after a stint in the pharmaceutical industry, I decided to take some night classes in programming and immediately found my calling. I actually ended up leaving the pharmaceutical industry altogether and founded a startup for about 3 years. And after that sort of petered out into just doing contracting work, I started a master's at CU, and after some use of the force, Professor Bradley Hayes convinced me to switch into the PhD program as the seminal student of CAIRO Lab. And so I'm technically in my 3rd year of my PhD, although it feels like the 4th year. So given that background, you might ask how I ended up in robotics. Well, that startup was focused on creating chat agents to help people more quickly generate analytics reports. So if you know anything about Tableau, think natural language for Tableau reporting. And when I met Professor Hayes in my first week of grad school, he really convinced me of the strong platform that robotics provides for human-computer interaction research. So I was never really intent on studying robotics, but I just sort of fell into it. I don't think that is very uncommon. And to me, learning from demonstration is perhaps the most intimate interaction between a human and a robot. I love the idea of teaching robots in the same vein as we teach each other, be it through narration, demonstration, or imitation. And so to jump right into it, this talk will first cover learning from demonstration. What is that all about exactly? A categorization of methods and approaches in learning from demonstration, and then cover how constraints are useful for learning from demonstration. And this will segue into why constrained motion planning is important for LfD and what constrained motion planning actually is, and introduce some of the current state-of-the-art approaches. I will then go into a deep dive on a paper called Task Space Regions, a framework for post-constrained manipulation planning that provides a really expressive way of representing constraints for constrained motion planning. And then very briefly, I'll touch on some of my current and future work that will ultimately constitute my dissertation. So let's jump right into it. Robot learning from demonstration. So for the few of you who are unfamiliar, robot learning from demonstration is a suite of techniques that enable layman users to program, quote unquote, a robot by example. And this usually requires a numerous number of demonstrations to generate a data set for a learning model. There are a number of input modalities. The interaction types include kinesthetic, where you're actually manipulating a robotic arm, imitation, or maybe the robot is observing a human, or teleoperation. And there's a variety of data inputs as well. These include raw observation of state, potentially constraints, goal indication, what have you. So some of the most important questions that I hope to answer are really like what was learned and how these skills are represented by these methods. But briefly, I want to touch on why is learning from demonstration useful? Well, the nature of collaborative robotic tasks hints at a need for more user-friendly mechanisms to train robots to be useful. Collaborative robotics are those working side by side with humans. They operate in environments where, the objects could be changed pretty consistently. There's a certain amount of coping with uncertainty, and perhaps the most important is an adherence to human expectations of behavior. And so traditional robot programming requires extensive engineering and software knowledge, and this prohibits the adoption of these smaller scale robots especially in environments with layman users. So the intuition is to just enable human beings or mimic how human beings teach each other. So it's important to note that learning from demonstration does not necessarily have a unique input type of data. Very, very commonly, you'll see end effector and robot joint configuration space data used, and sometimes object relative space. But there's a variety of other types of input data that can be used to train learning models. And this is an important point to note when I reach the discussion about integrating constraints into learning from demonstration. But broadly speaking, the representative—
Sorry to interrupt you, Carl. It seems like you might be covering your mic sometimes. I don't know if you're moving your hands, but I'm getting like as if you're talking.
Yeah, I always forget that my mic on the Lenovo ThinkPad is on the touch.
It's no problem.
I'll try and
try to never do it again ever.
I'll try to just use the mouse. I think I can click. I think I can use the rolly. So does this sound better? Okay. So jumping back in, broadly speaking, the representative models learned from demonstration can fall along a generalized spectrum of abstraction. And so at the very narrowest end, or the most highly fitted, you have what is essentially behavioral replay. You're just repeating exactly what you showed the robot. But at the opposite end, you are sort of in the realm of like task level or goal level learning or hierarchical learning. And many of these learning from demonstration models really kind of have a mixture of both. So they sort of encompass some low-level type of trajectory production and ideally some higher-level representation that maybe allows these models to generalize. A framework that I really like is provided by Harish Ravichandar in a review that he released in 2020 that continues Brenna Ardall's survey that classifies learning from demonstration methods essentially by their learning outcome, which I find to be a powerful way to organize these methods. This is certainly a more categorical approach than a simple spectrum of abstraction, and obviously it has its shortcomings, but I think it best captures the nature of the field as it currently stands. And so in this categorization, there are essentially three types of models for LfD. There are policy-based, cost or reward-based, and plan-based. Policy-based learning from demonstration assumes the existence of a learnable function, i.e. the policy that produces the desired behavior. So essentially, given a set of demonstration data and whatever learning technique you employ, you are trying to learn some function that produces your desired action. And there's generally two modes of output in policy-based learning from demonstration. There's trajectory-based, in which the policy maps directly to trajectory space, or low-level action, where the policy maps to low-level control signals, such as like joint torques. And now these methods assume a variety of learning techniques, two of the main ones being fitting some sort of dynamical system to the data, or Bayesian inference methods. So as an example of policy-based LfD, Peter Pastor's paper, Learning and Generalization of Motor Skills by Learning from Demonstration, uses a learning system to select from a library of motion primitives that can be used to produce a robot trajectory or set of controls to execute a desired skill. A dynamic movement primitive is a dynamical system, usually a linear differential equation spring system, fitted to an example trajectory, which can then be used to reproduce a new trajectory alone or in combination with other primitives. So in the case here, this function here and the weights associated with the dynamical system are essentially the policy directly learned that can then produce robot trajectories. Cost and reward-based learning from demonstration methods assume the existence of an optimizable cost function that can ultimately dictate the ideal behavior. This might also include a learning model T of the world dynamics or transition probabilities that define the difference between model-based and model-free learning. But essentially, the focus is on learning this cost or reward function. And there are two main sort of subcategories in cost and or reward learning LFD. There's trajectory optimization methods, which essentially assume that the expert demonstrator is minimizing an unknown cost function. But in practice, usually demonstrations are used to infer parameters for a pre-chosen parametric function. And probably the larger category is that of inverse reinforcement learning, which represent a broadly applicable set of methods that learn a cost or reward function directly from input data. And once this cost function is learned, you can use classical reinforcement learning techniques to then produce or derive a policy that produces your optimal actions and behavior. So in a paper submitted by Halit Ben-Sue called Learning from Demonstrations for Shaping through Inverse Reinforcement Learning, this introduces two variations of a novel take on combining reward shaping with inverse reinforcement learning. And for those who don't know, reward shaping is a mechanism that provides an intermediate signal or reward or heuristic during state transitions that augment the traditional environmental reward that is typically much more sparse in reinforcement learning scenarios. And so the learning process is as such. You collect a set of demonstration data from users, and then you recover a linear potential function using inverse reinforcement learning that becomes this reward shaping potential function. And then you use that potential function to shape the learning process for a traditional reinforcement learning episode. Plan-based LFD assumes higher levels of task abstraction, and the intended output of the learned model is either a sequence of high-level actions or even a hierarchy of actions and plans. These types of models are often used for more complicated tasks that have ordering constraints and subtask interdependence. In George Konadaris's work, Robot Learning from Demonstration by Constructing Skill Trees, demonstration trajectories are segmented into more primitive skills rather than learning a model based on the entire trajectory. This allows specific segments to focus, say, on goal-oriented or policy learning approaches, while others might focus on movement primitives. It allows skill segments to also achieve varying levels of abstraction. And lastly, CST, as he calls it, supports the merging of skill chains into skill trees, which allows it to deal with collections of trajectories using different component skills to achieve the same goal. So in essence, it allows for a mechanism to sort of combine all these different primitives, depending on whether they're policy-based or dynamic movement primitive-based model, and sort of string them together to solve more sophisticated problems. As with any categorization, there are models that do not cleanly fit into the given paradigm. And keyframe LFD is a model that, to me, doesn't necessarily fit cleanly into the previously presented categorization, but it perhaps most closely aligns with policy-based LFD in that it does produce, course trajectory. But in keyframe LFD, you first capture user demonstrations, and then you downsample the trajectory data into keyframe points, as you can see here, which then allows you to create what is called a sequential pose distribution. In other words, it's an ordered sequence of statistical distributions that you can then sample in order to create a very sort of coarse representation of a demonstrated skill. These distributions can further be shaped by using higher level information during and after a demonstration, as I demonstrated in my own work. So given all these wonderful approaches that cover a diverse array of machine learning and statistical learning approaches, it's worth asking, well, what is missing? So as I mentioned previously, one of the most common forms of input data is trajectory demonstrations that capture robot state data. And while these input modes of demonstration have a low overhead and provide a very precise instantiation of the skill you're intending the robot system to learn, they have limited information bandwidth about what they're actually really communicating to the learning system. Relatedly, when humans teach each other, there are many implied constraints, which your robot really doesn't have the ability to infer, and trying to learn those constraints can be very difficult. And so this idea of maybe a common sense from demonstration requires a prohibitively large number of demonstrations, which you probably don't have time for and that you probably still shouldn't trust. So alluding back to the point I made earlier in the discussion about input modes for LfD, there exists a possibility of augmenting these traditional input modes with richer information that allows the learning system to produce a model that much more closely resembles the intended ground truth model that the human user is trying to communicate to the learning system. And while it is possible to learn constraints from demonstration, the big challenge is that the number and nature of prohibitions is likely to be much greater than the number of prescriptions. In other words, it's much easier to show what to do than not what to do, because the space of things that you don't want the robot to do are much, much larger. So the key idea is to instead have human beings directly communicate these prohibitions to the robot system through other modes of communication like narration or augmented reality, and perhaps encode them in such a way that are usable by learning from demonstration methods. And this is something that I introduced in an algorithm called concept-constrained learning from demonstration, which essentially augments the keyframe-based LfD method that I just introduced by shaping the sequential pose distributions through a rejection sampling mechanism to ensure that those pose distributions are representative of the constraints on your system. And so this provides a good segue into the other major area that I will present, and that is constrained motion planning. And so you might be asking, well, why is constrained motion planning important for learning from demonstration? Well, if we are to incorporate constraints, whether they're learned or communicated, it is essential that these constraints are satisfied during skill execution. And some LfD models rely on unconstrained motion planning algorithms to produce these robot trajectories. The example being keyframe LfD or some of the higher level learning from demonstration methods I introduced. So the key motivation is that constrained motion planning algorithms give LfD models that rely on motion planning for trajectory production guarantees that any produced robot trajectory will be constraint compliant. So this begs the question, well, what is constrained motion planning? Constrained motion planning is a fundamental problem in robotics and really beyond, where you're having some sort of agent, whether that be physical or in software, what have you, that needs to plan some sort of trajectory of, say, controls or states that adheres to a specified set of constraints on the behavior of that agent. And in an ideal world, that means finding a path along what is called the constraint manifold that is representative of the constraint set in order to achieve this successful trajectory. The biggest challenge in constrained motion planning is that very often the analytical definition of a manifold is generally unknowable. So if you look at this picture on the side here, you see a sphere and say like a 3D Euclidean space. Now a sphere is a manifold, and maybe that represents, a geometric constraint. You have to stay on this sphere. But an orientation constraint that is represented in a 7 degree of freedom arm has no real definable or no analytical definition that you can just draw upon to sample points directly. And so as a primer, it is important to understand, well, what really is a manifold, and specifically, what is a constraint manifold? So topology, in a one-sentence summary, is the mathematical discipline that studies shape, mathematical shape, with a fairly lenient notion about what it means for two shapes to be the same. And by definition, manifolds are topological spaces with an important property, that is that a manifold has a neighborhood. Any point on a manifold or on this shape has a neighborhood that is homeomorphic to a Euclidean space of dimension n. In other words, when you zoom way close up to a manifold, it gives the appearance of flatness. So using that sort of same sphere analogy, the more and more you zoom up to a specific point, the more and more the surface of that manifold looks locally Euclidean or flat. These local Euclidean spaces are known as charts, and the collection of these charts and the differentiable transition functions that allow you to jump from chart to chart constitutes what's called an atlas. And that right there is the very definition of what a manifold is. But more importantly, manifolds can represent restrictions of the agent or robot configuration, assuming you have a system of constraints that evaluate those things for compliance on an embedding space, usually the configuration space key of the robot. In other words, a constraint manifold can be thought of as the set of all agent or robot configurations such that the system of constraints evaluates those points to be equaling 0, implying constraint satisfaction. As a visualization of what a real constraint manifold might look like, in this 3-degree of freedom 2D arm, the constraint is that the end effector must always be touching this line. And the feasible points in this robot's 3-degree of freedom configuration space are these blue regions. And with all that out of the way, hopefully I haven't bored you guys to death. It's also important to identify what types of constraints can be used to define a constraint manifold. So robotic systems are generally classified into two types of systems as defined by the differentiable constraints placed upon them. The first is called the holonomic system, which are constraints or is defined by constraints on just the position of the configuration of the system. And the other is non-holonomic, which at best allows for a differentiable relationship between states and the inputs of these constraints. And as they relate to time, holonomic constraints have two main types. The first is what's called scleronomic, which are constraints that exclusively use the coordinates of some space and are not dependent on a time variable. And lastly, rheonomic, which just means you are including a time variable. So most of the papers presented within exclusively focus on holonomic scleronomic constraints, those that are differentiable to position and not time dependent. Such constraints cover many usable constraints on robot behavior, such as position, orientation, and relative distance and relative orientation to objects in your environment. So the challenge with generating what is known as a geodesic path, or a path along a manifold, essentially a trajectory or a motion plan along a manifold, is ensuring that points are adequately close to your implicit constraint manifold. Now, there are approaches that exist to optimize a given trajectory that utilize efficient optimization solvers, such as TrajOut, Chomp, and Stomp. And these have the potential to incorporate constraints and sort of piggyback on the efficiency of the optimization solvers that they do use. However, a limitation of these approaches is that any given trajectory that you're optimizing might not be feasibly optimized to be constraint compliant, even though there does exist a solution to your constraint planning problem. Secondly, constraints must be expressible in a way such that they conform to the nature of the optimization methods used. For example, in CHOMP, obstacle collisions are expressed as a potential field term in the optimization step, but your implicit constraint manifold might not easily be able to provide such a gradient efficiently to be used in this optimization step. So to overcome some of those shortcomings, it would be nice to be able to employ the benefits of sampling-based motion planning that gives us guarantees of asymptotic optimality and a solution guarantee if a solution does exist for your planning problem. And to use a sampling-based motion planner, you need to have some way, as is in the name, sample a point, but in this case, a point that exists on your constraint manifold. There are three main approaches to doing this. The first is through rejection sampling, where you simply just take a random point and test whether or not it is constraint compliant. But this is really only feasible if your manifold is of the same dimension as your embedding space, and ideally covers a large portion of the space that you're stochastically sampling from. The second and the most commonly used one is to project a random point onto your constraint manifold, which does require some notion of a distance away from that manifold and ultimately some sort of gradient. And lastly, there is task-based sampling, in which you sample a point in task space in which you can analytically calculate for constraint compliance. And you use inverse kinematics to project it back onto your constraint manifold with a guarantee. However, the problem is, due to the null space of this mapping, this can result in joint space discontinuities, and you also lose asymptotic optimality. So most of the sampling-based motion planners that I'm going to present, and there are three of them that sort of kind of build on top of each other, incorporate manifold projection techniques into tree-based sampling-based motion planning, specifically rapidly exploring random trees. The reason the reason these papers have traditionally gone for tree-based approaches is because they are single query and they're usually a bit more efficient in terms of the number of samples that they actually have to evaluate. So jumping right in the late Mike Stillman's work on task-constrained motion planning for robot joint space, Mike takes the notion of what is called a first-order retraction of a topological space onto a subspace that is your manifold, and fits that into the mold of the RRT sampling-based motion planner. Essentially, the growth mechanism is such that a random point, Q-random, is chosen, and then you try to find the nearest point in your tree to this random point that is off your manifold, and then you extend from that node, that leaf node of your tree, to some arbitrary step size to generate a QS, and then you perform a first order retraction or projection back down onto your manifold. And the assumption is that the interpolation between this nearest point and the newly generated constraint compliant QS prime point is such that you are still within the tangent space or the locally flat region or local Euclidean space of Q near, such that the interpolation that is then used to traverse from point to point remains approximately on your manifold surface. The second method uses a more advanced notion that is introduced by Bio Kim, and this is called tangent bundle RRT. And the idea is, if you recall, that manifolds by definition are locally homeomorphic to Euclidean space. And so by assuming that within some radius around a point, that the tangent space around that point is a good approximation of your manifold, and you can simply grow your tree in the tangent space and not worry about projecting every single point down onto your manifold. And so by doing this, you can create sort of a sequence of, with tangent spaces in which you're building trees that you then transition to another tangent space, build your trees efficiently, transition to another tangent space, and build your tree more efficiently. Related to tangent bundle RT is an RT-based approach called Atlas RT, introduced by Leonard J.A. and Joseph M. Porta. And essentially, Atlas RT takes the notion of adopting the atlas and chart definition of a manifold to its logical end. It's very similar to tangent bundle RT, in that again, it treats each local tangent space as a chart or a local Euclidean approximation of your manifold. And it will only transition to a new tangent space so long as certain criteria are met. So this is where the differential comes in. The transition criteria are much more strict. And it's essentially testing for curvature away from your manifold, as well as some distance away from the point you're using as the center of your tangent space. This ultimately makes for a more efficient approach because it reduces the amount of tangent space overlap that makes tangent bundle potentially inefficient. So more recent techniques forgo the use of these analytically approximate techniques, at least during runtime, by using learning approaches for estimating, using deep learning approaches for estimating the next point to extend towards during the RT graph construction. In Ahmed Qureshi's Constrained Motion Planning Networks X, 2 deep learning networks are used to provide extension points for the growing RT portion of the algorithm. Essentially, you have a neural generator that produces from a given point a Q next. You then also have a neural discriminator that just ensures that that Q next is still along the manifold. And if it's too far away according to some distance criteria, then it will employ the traditional projection technique that Mike Stillman developed. Essentially, you're offloading a lot of the projection portion of the planning problem to train this neural network that then allows during runtime or on query time a much more efficient mechanism to produce constraint compliant points in your tree growth. But it remains to be seen whether these approaches have the flexibility of these previous methods I introduced to be able to use just a brand new set of constraints that maybe the robot system hasn't used before. And finally, it's important to note that all of the previously presented constrained motion planners operate on a single set of constraints, with the assumption that the start point and end point are generally the terminal points of your skill. However, many robot tasks have changing constraint requirements over the trajectory of skill execution. So for example, an orientation constraint might only be pertinent once you actually pick up the cup. And so during the sequence of that motion plan, that orientation constraint only starts applying at some time down the execution of the trajectory. And so this introduces what is called the sequential manifold planning problem. And in Peter Englund's work, sampling-based motion planning on manifold sequences, a simplified version of this problem is solved first by identifying the intersection of simple manifolds, in this case, parabolas and cylinders, and then using the aforementioned constrained motion planning techniques to essentially create sort of like a piecemeal or sequential trajectory where you're adhering to one set of constraints, then a different set, and then another set. And this problem here is really essential to solving the sequential changing constraint set learning from demonstration algorithm that I developed called CCAIRO. So before I dive into the details of this paper, I want to emphasize that my own work requires not only solving the sequential manifold planning problem for skills learned from demonstration, but also trying to come up with like a human intuitive mechanism to express constraints that make sense to users. And the reason I chose this paper is because Dmitry Berenson essentially extends Mike Stillman's work but introduces this notion of what's called the task space region that is a really expressive and intuitive way of expressing these holonomic, scleronomic constraints for motion planning. So let's jump right into this paper. A task space, first of all, let me first say that task space is generally referential to the end effector position and orientation, which sometimes extends to relative position and orientation to environment objects. It's generally a more human intuitive mathematical / geometric description of the robot's arrangement than say like trying to understand a robot's position given joint angles. And a task space region, or TSR for short, is essentially a matrix representation of the rotation and translation of the end effector or of an object, essentially a transformation, that is also closely tied to what is called this bounds matrix. So essentially what this is saying is that, say you have an orientation constraint on this can right here. Well, the transformation or the translation and orientation of the end effector has to be as such within certain bounds of translations and rotations in order to be constraint compliant. These task-based regions also can be chained together to create virtual extensions of the end effector. It's almost as though you're virtually like adding links to a robot arm. That can provide kind of a unique way to express like relative positions to objects that might also move as you manipulate them during a planning problem, like a swinging door or opening a door. So let me just real quick kind of describe this picture here. So essentially we have some global frame of reference, 0 or O. We have the transformation from that reference to the end effector's base. And given the expected end effector position relative to the object, we can use that inverse to get the current end effector's offset. But the most important point here is what this transformation here represents. And is essentially saying that we have some task-based region, orientation, and position with some given bounds of allowable error or wiggle, so to speak. And this transformation essentially defines how far away the current end effector is for a sample point is from the idealized end effector orientation. And that ultimately gives us a notion of a displacement away from a constraint that we can then use to create essentially a task space error that it will, as you'll see, become very important in the projection step for the constrained motion planning that this paper uses. So as I mentioned earlier, task-based region chains can be linked together to create essentially what is like a virtual manipulator. So as you can see here, we have this robotic arm that essentially creates a virtual joint by grabbing this handle, which now then is inexorably tied to this door handle. And so it's a really neat way to essentially define a relative orientation of an object that might actually be dynamic when you manipulate it, but all relative to just the robot's configuration. So it's again, this task-based region is a really descriptive way to represent orientation and positional constraints. So given this task-based region representation, I want to go into a little bit greater detail into the constrained bidirectional rapidly exploring random tree algorithm developed by Mike Stillman and extended into this framework by Dimitri Berenson. And as a quick primer, I just want to remind people what a bidirectional RT algorithm essentially does. And as you can see in this video, you have a goal and start location, and essentially the algorithm just has two generic RT trees growing towards each other. And as soon as there's a feasible connection to be made amongst those trees, then you've solved your motion planning problem. You've discovered a path from start to goal. The big difference in the constrained motion planning step is this extend function and the notion of what it means to add a new point into your tree. So to jump right in, this algorithm is essentially almost verbatim how traditional bidirectional RT operates. The only difference highlighted here in bold is this constrained extend function that encapsulates all the task-based region and projection-based techniques that are occurring in this algorithm. But to cover this as quickly as I can here, because I'm running a little bit over, essentially you swap back and forth between your two goal and start trees. And given one of your trees, you generate a random configuration and extend that tree towards that random configuration using this constrained extend function. And this will ideally produce just an extension point that is along your constraint manifold that you can then try to extend the nearest point on your other tree towards. And you do this over and over and over again until hopefully your trees converge at a point that are connectable and that you've solved the path. So essentially you're growing two constrained trees towards each other. And once they're connectable, then you have a solution or a guaranteed trajectory that is constraint compliant. So tying into the constrained extend function, this is very similar to the paper presented by Mike Stone. Essentially, you have this Q near, you extend towards some arbitrary random target, a certain Q step size right here, and then you project back down. And you repeatedly do this, and as you see, it slowly builds a geodesic extension off your current tree. And I won't go into the details, but there are some tricky terminating criteria to make sure you're not extending for forever. But the important point is deeper into this constrained extend method, we have a function called ConstrainedConfig. Now that is essentially what is producing this projection set right here. So the constrained config functions are usually problem specific because this is where you get into the notion of incorporating or grabbing your task space regions or task space region chains for a specific problem. And essentially what they're doing is they're collecting the task space regions, producing a target point, and then finally projecting that point down. So before I talk about how this projection actually works, I want to introduce to those who aren't familiar something called the robot Jacobian. Now, the robot Jacobian is a matrix of partial derivatives that provides a linear transformation of your joint space velocities to the end effector linear and angular velocities. So it's essentially a transformation or mapping between joint space and task space. What you'll see here real quick is this E matrix. This is used essentially because the Jacobian is usually in angular velocities, but the task space regions are represented in like Euler angles. So you need to have an additional transformation so that this Jacobian is then usable as a mapping function for your task space region and eventually mapping a task space error into a configuration space error. So this jumps us finally, as we've tunneled all the way down to sort of the core part that really makes this algorithm, this motion planner, constraint compliant. And that is this ProjectConfig function. This is or it's also called the pseudo-inverse Jacobian projection. And it's pretty straightforward. You see here, given that task space region definition that defines your constraint, you essentially produce a task space error. If that task space error is within some epsilon, then the point that you're testing for is essentially approximately on your manifold. But if it isn't, then you snag the Jacobian of your current configuration, generate the pseudo-inverse that inverts this mapping so that you can move your class space error into a configuration space error, which can then act as an update term that moves your current configuration ideally to a new configuration that is closer or ideally onto your manifold, your constraint manifold. So there are three ways in which Dimitri evaluated this. The first was just a simple table clearing task that just shows kind of a proof of concept that this task space region representation is feasible and that it works. The second was a maze evaluation problem, which essentially restricted the end effector to have a pen on the surface of the table, which then enforced the RRT portion of the planner to have to solve this difficult narrow corridor problem. The third approach, and this is probably the most interesting, is combining this task space region and this projection sampling technique with rejection sampling of torque violations. And so what this allows this planner to do is essentially carry a heavy weight that might violate robot torques. And then given how close that end effector is to one of these surfaces here, plan for sliding that weight along that surface such that it won't violate torques, but also maintains a certain orientation. So I thought that was a pretty powerful demonstration of this framework. And so I'm pretty over time here, I apologize. So I'll just very quickly touch on my current and future work. My first paper introduced an algorithm called concept constrained learning from demonstration. And essentially this augments keyframe learning from demonstration by encoding constraints as grounded Boolean state classifiers that can be used to shift those sequential pose distributions so that they more appropriately represent, this constraint manifold. And then essentially you can use that to generate a coarse constraint compliant trajectory. But I still need constrained motion planning to ensure that the actual motion plans between these waypoints remain constraint compliant. And related to different modes of interaction and input data, in conjunction with Connor Brooks and Matthew Lubers, we developed an augmented reality system for constrained learning from demonstration we call ARC-LfD that allows you to visualize what the CC-LfD model will produce and see which constraints are assigned, and then interactively and iteratively update these constraints and have the model update so that you can visualize how the skill might adapt to different constraints. I'm currently working on a sequential manifold planning problem that is learned through learning from demonstration. The idea is to take this constrained keyframe graph from CC-LfD and use the areas that the constraint sets change as my learned manifold intersection region, that then allow me to use a constrained motion planner to solve this sequential manifold planning problem for a more sophisticated robot task that was provided by a human user. And then real quickly, some future projects. This summer, Himanshu Gupta and I will be focusing on learning object goal associations from demonstration in order to improve social dynamic navigation. So the idea is that human beings in a crowded environment might be associating with known or classifiable objects, and perhaps in knowing how they interact with those objects, if those objects are seen in a new environment, that might allow this robot to improve its social navigation abilities. And then lastly, I've been in discussion with Akib Tabrez and Matthew Lubers about a project that will enable the robot to demonstrate counterfactual constraint assignment to the user to show the effect of adding or removing constraints and what that might do to the expected skill execution. So this is kind of a fun project because it'll combine CCLFD, my algorithm, sequential manifold motion planning, and the ARC LfD interface into kind of this single home run project that hopefully caps off my PhD dissertation work. All right, I reached the end. Thank you guys so much for listening. And if you have any questions, I'm happy to field some questions in the limited time remaining.